Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I hope you're all fine and keeping safe. Today we are going to start a new chapter of the unit Circulation. In this chapter, we are going to discuss the distensibility of different vessels and the functions of arterial and venous systems. So let us begin. Let us first understand what is meant by distensibility. Distensibility is the ability of any vessel to stretch or distend when pressure is applied. So, looking at the definition of vascular distensibility, it is the ability of a vessel wall to expand and contract passively with changes in pressure. Dear students, you might have noticed that I laid special emphasis on the word passively. Passively means that there is no involvement of the nervous system or any kind of hormones. This distension, that is expansion or contraction, is merely due to the changes in pressure within the wall and does not involve any kind of nervous or hormonal regulation. What is the use of this distensibility? What does the body gain from this distensible nature of vessels? Well, first of all, it allows for non-pulsatile flow. What is pulsatile blood flow? Pulsatile blood flow means blood flowing in pulsatile manner. That is, the blood would flow during the systole and not flow during the diastole. But this is not the case in our body. There is always a continuous flow of blood, whether the heart is in a contractive state or in a relaxed state. This is thanks to the very distensible nature of our vessels. Remember that all vessels are distensible. Some vessels are more distensible than the others. Veins are 8 times more distensible than arteries. What is the reason for this? Please bring to mind the anatomy of both vessels, veins and arteries. You might remember that arteries are like thick rubber bands. They have very thick elastic tissue within their walls, while veins do not contain as much elastic tissue as arteries. So what do you think? Which of these two vessels is more easy to distend or stretch? Yes, you're right. The veins are easier to stretch as they have less elastic tissue, while arteries are more difficult to keep distended as the elastic tissue in their wall tends to recoil and bring them back to their original shape. So, both veins and arteries are distendable to some extent, but veins are 8 times more distensible than the arteries. Let's have a look at another definition of vascular distensibility. This definition states that fractional increase in the volume for each millimeter mercury rise in pressure is called distensibility. Now let us understand what this definition means. To understand this, I'll give you an example. Remember, this is just a made up example and it does not apply to all blood vessels, but it is just for your understanding. Suppose we have a blood vessel which contains 10 milliliters of blood. If you stretch this blood vessel with the force of 1 millimeter mercury, you might be able to accommodate 1 more milliliter of blood into it. Do you understand? You had a blood vessel which initially had 10 milliliters of blood in it. No more blood can be put inside it. But if you stretch this blood vessel with the force of 1 millimeter mercury, you might be able to put 1 more milliliter of blood into it. This is known as distensibility of a vessel. So, according to this formula, this definition, the formula for vascular distensibility should be increase in volume divided by increase in pressure multiplied by original volume. So, to better understand this formula and this definition, let me give you an example which might hit quite close to home. Let me take you back to your childhood. You might remember your birthdays when you used to blow balloon after balloon to decorate your house. Well, you might remember you came across two types of balloons. Some were new with very thick elastic walls and were very difficult to blow into. On the other hand, you had some old balloons which were quite thin and worn out and had very little elasticity in their walls. They were quite easy to blow into. So, these two types of balloon are shown here depicting two types of blood vessels. The red balloon seen here is new and has a lot of elastic tissue in its walls, so it depicts the arteries. While the blue balloon you can see in this picture is old and thin and worn out with very little elastic tissue in its walls and is very accurate to depict the veins. Now let's do an experiment with these two balloons. Suppose before starting the experiment, both the balloons are not yet inflated and hold a little amount of air in them. The pressure within the walls of these balloons is 0 millimeter mercury. Now, if we blow into both of these balloons with the same amount of pressure, let's suppose 100 millimeter of mercury, what are the results we are going to see? Yes, this is how it is going to be. When both of these balloons are blown into with equal amount of force, we will see that the new red balloon holds way less volume as compared to the blue balloon. This goes on to show that tissue having a lot of elasticity is less distensible as compared to the tissue having lesser elasticity. So, arteries and veins, when distended by same amount of pressure, hold different volumes. Arteries hold lesser volume as compared to veins because of their elastic nature and elastic recoil. I hope you understood. Let's move on. Hopefully, now that you have understood what is meant by distensibility and what is the difference between the distensibility of arteries and veins, let's apply this knowledge to the working of arteries and veins. Do remember, both arteries and veins are distensible, but arteries are less distensible as compared to veins because of their elastic recoil. Now, let me take you back to the first slide of my lecture where I mentioned that it is thanks to this ability of a vessel to distend that we have non-pulsatile or continuous blood flow in our body, which means that not only does the blood flow during ventricular contraction, but this blood flow is also maintained while the heart is not pumping during ventricular relaxation and diastole. Now, how does that happen? During ventricular contraction, the ventricle pumps its blood out of the ventricle into the aorta and to the peripheral blood vessels. The blood which is being pumped out of the ventricle into the aorta causes the aorta to expand and distend under the pressure. This distension allows aorta to hold a specific volume of blood within its lumen during ventricular contraction. Now, during the ventricular relaxation, when the ventricle is no longer pumping blood into the aorta and the aortic valve is closed, this distended aorta recoils backward toward its natural state. When aorta recoils, it pushes this blood towards peripheral arteries, thus maintaining continuous blood flow to the periphery even when the ventricle is relaxed. So this is how the distension of aorta and its recoil ensures continuous flow of blood through the vessels within the body. At the same time, the veins, which are 8 times more distensible than the arteries but do not show much recoil, have the ability to stretch and hold large amounts of blood. This is the reason that at any given time, 64% of your blood lies within your veins. So, thanks to distensibility, veins can act as reservoirs of blood. Now that you have understood what is meant by vascular distensibility, let us move on to another definition, which is known as vascular compliance or capacitance of a vessel. Do not confuse it with distensibility. Where distensibility was the ability of a vessel to stretch or distend under pressure, compliance is the ability of a vessel to actually hold volume. As the name applies, vascular compliance is the total quantity of blood that can be stored in a given portion of a circulation for each millimeter rise in pressure. The formula for vascular compliance is increase in volume divided by increase in pressure. Veins are 24 times more compliant than arteries, which means veins can hold 24 times more blood as compared to the arteries. Two types of compliances can be seen in blood vessels: early compliance and delayed compliance. Early compliance can be seen in aorta when the ventricle pumps and pushes its blood into aorta, causing the walls of aorta to stretch and hold volume within its lumen. Immediately following this stretch in the wall of aorta, we can see that aorta contracts, forcefully pushing the blood into peripheral arterioles. This contraction immediately following a stretch is known as early compliance. This is due to the elastic recoil of the aorta. On the other hand is delayed compliance. Delayed compliance is seen in cases of sustained pressure. And contrary to immediate compliance, blood vessels relax when faced by sustained pressure and do not contract like in immediate compliance as seen in aorta. So what is the mechanism of delayed compliance? When a vessel is exposed to increased volume, at first it exhibits a large pressure within its walls. But when this pressure is sustained, then after a delay of few minutes, the smooth muscles of the vessel wall stretch and allow the pressure within the walls of this vessel to return to normal. Now, to better understand this example, I would like you to look at this graph. Suppose we have a blood vessel which has some amount of blood within it, and this blood causes the vessel wall to stretch, which is indicated by this initial length of the vessel wall, and this stretch causes this much amount of pressure in this wall. Now, if you inject more blood within this vessel, you will see that this additional blood causes the vessel wall to stretch, which can be seen by this hike or upward movement of the graph over here. And if this blood is allowed to stay within this vessel, this sustained stretch can be seen with this straight line. Now let's see what happens to the pressure within the vessel wall. Immediately after injecting blood, you will see a sudden rise in the pressure in the vessel wall. But this sustained stretch will cause this pressure to fall back towards normal over time. Now, what causes the pressure to fall back towards normal? It is the readjustment of cross bridges within the smooth muscles and the stretching of the non-contractile part of the smooth muscle, which allows the vessel wall to accommodate this new amount of blood within its lumen without increasing pressure. So, from this graph you can see that if a blood vessel is faced with sustained stretch, it will first experience a rise in pressure, but after some time the smooth muscles will readjust and creep and stretch and allow the pressure to fall back towards normal while still maintaining or accommodating the additional volume of blood. So let's study the same phenomena with a very interesting example. Suppose one day on your way to school, you see a tree, and you, being the scientist you are, decide to conduct an experiment. You identify a low-lying branch and label it A. What you do then is you tie a very heavy weight to this branch. This branch sags under the weight to a new position. Let's label it B. You record the time to be 8 a.m. and you move on to your school. On your way back, when you pass the same tree, you now notice that the branch of the tree has sagged even lower to a new position. Let's call it C. So what has caused this branch to sink or relax to a lower level C despite the weight being the same? This can be explained by the phenomena of stress relaxation, which states that if a stress is sustained, the tissue relaxes. Let's look at another example from your book. Suppose we have a vessel which is closed at both ends, and this vessel contains a certain amount of blood within its lumen, and the blood which is present in this vessel is exerting a specific pressure on the vessel wall, which is around 5 millimeter mercury. And now what you do is you inject a large amount of blood into this closed vessel. This additional volume of blood would cause immediate rise in the pressure within the vessel wall. The pressure will rise from 5 millimeter mercury to around 12 millimeter mercury immediately following the injection. But as the time passes, after a few minutes, this pressure will fall back to around 10 millimeter mercury. This is due to the readjustment of cross bridges within the smooth muscles which make up the vessel wall. This smooth muscle relaxes and readjusts to accommodate this additional volume of blood without much increase in the pressure. The pressure which falls back does not return to the initial stage. This is because there is, after all, some additional amount of blood added into the blood vessel. But still, it is a lot less than the pressure which resulted immediately after the injection. This is known as delayed compliance. So, summing this up, blood injected in the vessel causes immediate elastic distension, but then smooth muscle fibers of the vessel begin to creep to longer lengths and their tension decreases. See, as you can see within this vessel wall, immediately as the blood is injected into the vessel wall, the vessel stretches, but after a few minutes it relaxes back and still holding the same amount of blood but with reduced pressure within its walls. So this is known as delayed compliance or stress relaxation, which is the relaxation followed by sustained stress. This stress relaxation is shown by all kinds of smooth muscle, the smooth muscles which make up the vessel walls, and even the smooth muscle which make up hollow organs like the bladder and the stomach. Now let's compare delayed stress relaxation to early stress relaxation or early compliance. As I told you before, early compliance is shown by aorta when it is subjected to immediate stress, when blood is pumped into it by the ventricle, and when the ventricle stops pumping blood into it and the stress is taken away, the aorta recoils and pumps the blood into the peripheral arterioles, and it is due to the elastic recoil property of aorta. But when a stress is applied to a blood vessel and this stress is sustained and prolonged, so what are the changes we see in the vessel wall is that immediately when this stress is applied, there is an increase in pressure, but as the time passes, this pressure falls back towards normal, and this is known as delayed compliance, and it is seen in cases of sustained or prolonged stress, and it is due to the ability of the muscles to creep or readjust their bridges and lengthen and accommodate larger quantities without notable or noticeable increase in pressure. Opposite to stress relaxation, there is this phenomena which is known as inverse stress relaxation. This is seen in cases of hemorrhage or bleeding. What happens is when a blood vessel is cut and the blood volume is moved out of the blood vessel, the volume inside the blood vessel decreases, and the volume which was stretching the walls of the blood vessel, since it is no longer there, the stretch on the vessel wall also decreases. So to accommodate this lesser amount of blood, the blood vessel tries to contract around the remaining volume of blood, so the pressure can be increased and this remaining amount of blood can be circulated efficiently within the body. So it can be seen in this graph that suppose there was a blood vessel with certain amount of blood in it, and this blood causes the vessel wall to stretch to a certain length, which can be seen here. Suddenly there was a sudden decrease in the volume of the blood due to some hemorrhage or blood loss, and the stretch on this wall was decreased, which can be seen with this sudden downward curve of the graph. And then this reduced volume was sustained, and the stretch on the vessel wall was reduced for a long time. So what happens to the pressure? So immediately after the hemorrhage, the pressure within the vessel wall falls, but after some time the smooth muscle contracts and readjusts itself around this reduced volume of blood and tries to bring back the pressure back towards normal, so that despite there being less amount of blood in the blood vessel, the pressure is increased, so this lesser amount of blood can be circulated within the body. This is known as inverse stress relaxation. Now let's study inverse stress relaxation on the same graph on which we previously studied stress relaxation. Now if a certain amount of blood is reduced from the same blood vessel, you will see an immediate decrease in the pressure. But after some time, the pressure begins to rise and reaches almost normal. This is known as inverse stress relaxation, and it is seen in the case of hemorrhages. Now let us study the importance of delayed compliance. Delayed compliance helps in accommodating extra blood or extra volume when it is necessary, and this is done through stress relaxation, and this is seen in the case of large transfusions or large intravenous administration of fluid. On the other hand, delayed compliance also plays an important role to adjust to decreased volume of blood by reverse stress relaxation, and this can be seen after serious hemorrhages during accidents or during surgeries.